So we have all of these idealized models of the world, and we have relationships between them. And what that all boils down to are the coordinate systems that we use to represent that data in, well, originally on paper and now in GIS models. So different types of coordinate systems that are used. We have the spherical globe that we talk about when we're modeling, and those are the geographic systems that you see in ArcGIS. And then you have the what are typically planar systems, though as 3D modeling becomes more visible and more prevalent in the world, I think you'll start to see things that are in between an idealized spherical model and a planar representation that you can print on paper. Maybe someday we'll have really crazy 3D projections that we can interact with in a virtual reality system. That would be pretty interesting and probably is not all that far away. But those are going to be your projected coordinate systems. Typically in the past referred to as planar or Cartesian systems. All right, so the most common geographic coordinate system that we see is the lat-long system. So that's based on the assumption of a rotational axis that goes directly through the North Pole, which if you have any experience with navigating by compass or any memories of elementary school geography, there's a relationship between the rotational axis of the Earth and the magnetic north, and in that they are close but not the same. So we're talking about the actual rotational axis of the model of the Earth. And then formed by this designated equator, which is a perpendicular plane through that rotational axis. And then an arbitrary plane chosen to run through the Greenwich Observatory originally. Funny fact though, it no longer does. So along with those major axes and planes, we have the minor increments of that. So a line running from east to west is a parallel. So if you took multiple slices running up and down that globe, they would not be straight, but in interests of, well, good thing I can't draw a straight line. There we go. These are our parallels. And then any line running between the North Pole and the South Pole is a meridian. So Greenwich is the prime meridian. It goes not at all like that, but kind of. And then you have all of the other minor meridians running around your globe. And when you show those on a planar map, like the one we were looking at a second ago, those grid lines become what's called a graticule. So you'll often see a graticule, and you can overlay those in ArcGIS. I think some of you have played with those already. They're a pretty common representation of latitude and longitude on a map, very familiar to most people who have practiced using actual paper maps, which are phasing out of the world, sadly, but also saving trees. So I don't love the annotations following me feature. I can turn that setting off. All right. So obviously a circle has 360 degrees. A sphere you could describe as 360 degrees in 3 different planes. But the way that we actually break it down is that from Greenwich, you can go 180 degrees in either direction. And between the equator and the poles, we break those up into 90-degree chunks. And then each degree is further broken up into minutes, which are represented by a single tick mark. And then each minute is divided up into seconds, which are represented by 2 tick marks. If I get a chance, I will show you how you do the math to convert between the two, but otherwise, I don't ever want to see positions in degrees, minutes, and seconds, because all you're going to do is convert them back into decimal degrees, because you can't easily do math with degrees, minutes, and seconds. And we don't get those out of a GPS anymore unless you tell your GPS to do it, which is a really painful process, because then you have to convert it back into a decimal degree to do anything with it. But traditionally, when we sailed the oceans with compasses and secants and things like that, we had minutes and seconds, and so we still use them. So your lines of longitude measure your east-west distance, but they are north-south lines. So it's can be confusing when you see descriptions of latitude and longitude. There are tricks out there for remembering which is which, and I should have tried to amass a selection of those tricks. Different things work for different people. For me, it's remembering the title of the book, Rowing to Latitude, which is about rowing around the coast of Alaska in an actual rowing frame vessel. So interesting book and an interesting story, and it helps me remember the difference between latitude and longitude. There was something in my elementary school about laying a ladder on the ground, but I got confused between the rungs and the size of the ladder. So if you guys can make that one work, go for it. So like I mentioned, that we have the convention of Greenwich, the prime meridian being 0, and you move 180 degrees in either direction. What this was meant to show was you go 180 degrees west, there's an arrow, or 180 degrees east. Oops, stop doing that. That translates, and I don't know if you guys can see the bottom of my slide. On my screen, it's cut off, which is not helpful, into negative and positive. So in a mathematical system where we're showing coordinates in a database, we don't have little E's and W's hanging out behind our data. We use negative and positive. So if you remember when you're writing down a latitude and longitude in Alaska, you are always going to have a negative longitude. If you forget the negative sign or you don't put a W, you're in Russia. And that's confusing. If you bring in your data and it shows up in Russia, the person who gave it to you forgot the negative sign or didn't think it was important, and they were wrong because now they're in Russia. Latitude is a little more straightforward because we're used to thinking of north as up, which if you think about it, isn't necessarily true. So flip that relationship around, and that could really start to mess with your head. But again, if you don't represent things with north and south, you use negative for the south because we're a north-dominated planet. And you'll also notice that those lines behave a little bit differently than the longitude lines, right? All longitude lines run through the poles, but latitude lines slice through the earth. So that has some consequences when we take that information and draw it on a paper map. One thing important to note here is that when you are using latitude and longitude systems, those are actually based on a model, right? We said we aren't using a sphere, we're using a spheroid or an ellipsoid. And so those are based on an angle that doesn't actually run through the center of the Earth. So when you talk about latitude and longitude, you actually technically have to talk about what kind of latitude and longitude. Most of the time you're going to see that ignored because what we typically use is the WGS84 and NAD83 systems, which are based on the same ellipsoid model, essentially, of the Earth. So if you see it without representation, unless it's really old data, you can typically assume that you have WGS84 or NAD83 lat long. So what do we use to define 0 degrees longitude? Specifically, what location on the planet, if you were going to go there and stand on it? You guys are getting close. It is in Greenwich. It used to be the Greenwich Observatory, but it's now 102 meters east of the Greenwich Observatory, which I love that fact because I think it really represents how we are continually modeling our planet and continually refining that model, and then finding out either that our models weren't good enough or that things moved on us. So if you're here for Greenwich, if you're going to build a building on the prime meridian, you might want to make it movable. All right, so convergence is a form of distortion that you get from projection, right? Any projection system that represents a spheroid on paper is going to have to distort that spheroid in some way. We've taken it and we've shredded it into little bits and flattened it out on a piece of paper. So for a geographic coordinate system, you're going to have what you call convergence, which is the fact that these longitudinal lines all converge into the poles, whereas the latitude lines transect the Earth in a parallel series of planes. So you start to see severe distortion as you approach the poles, which are theoretically not arbitrary points, right? The poles represent a physical force on our Earth, and the reason that we use them is because all magnets point towards those poles, and so we could use that for really early navigation. But when you're talking about modeling something on a theoretically uniform ellipsoid, how much importance should those points really carry? Well, that's an interesting question when you start talking about modeling things near those points, right? We've got a fairly consistent relationship between points along the equator, and then that relationship begins to change as we get to the poles. So you can imagine if you're trying to model something on the North Pole, that process is going to look really different than the modeling process for the equator. And so that's where we start to get into a lot of different models for planar coordinate systems. So at the equator, we have approximately 110, 111.3 kilometers between each line of longitude, and then obviously at the idealized pole, there would be a theoretical 0 kilometers. So watch out for those longitudinal lines at the pole. And when you see this represented on a flat map, we've taken what are actually converging spheres that are started out as spheres, and then they became ellipses, and then they became really skinny ellipses, which is the opposite of an oblate ellipse, and I've forgotten that word now. I'll try to put it back in. But then we put it on a piece of map, and this is the historically and globally infamous Mercator system. It's one of the earliest attempts at, or at least the most well-known early attempts at representing our ellipsoidal Earth on a flat map in a defined fashion. But it has some interesting drawbacks and some really interesting effects in a geographic sense, but also in a social political sense. So Mercator takes a lot of heat these days, some of which is probably legitimate. So something to consider when you're representing your maps for the world audience. So kind of a little sidestep here, something really interesting to understand about navigation and the effects of figuring out navigation in our world. For a long time, we used these planar maps, a lot of them based around the Mercator system, which, as you remember, distorts the physical geometry of the world that it's representing in order to put it on a piece of paper. So when you put it on that piece of paper, you've now misrepresented the distance between any 2 points. So what we actually use now for navigation are great circle routes, which are calculated to fit around the Earth's ellipsoid. So I wish that we had one that represented the path through Unimac Pass, but if you'll notice, if you shifted this over just a little bit and you left the north or the west coast of America and you headed into Asia, as many things do, or probably actually the other direction more often, the best great circle route for transit from Tokyo and other places of production to North America is actually through Unimac Pass in the Aleutian Islands. So we get huge amounts of shipping traffic through Unimac Pass, and that was actually one of my first hydrographic survey projects, was updating the charts for Unimac Pass. So that's the impact of great circle routes on our real world. And they've also hugely increased efficiency of travel. Also, other than nautical travel, they're used really heavily in flight path planning. There was actually for a while a huge amount of traffic through Fairbanks, partly because there was a refinery there that refined avgas, but also because Fairbanks was on a great circle route between, again, North America and parts of, I think, a little bit further north. I think they were heading into Uzbekistan and places like that a lot of the time. And there was actually a shift about the time that the refineries in North Pole stopped producing avgas. There were some political changes in the areas where they were flying into, and they shifted a lot of those cargo transportation flights to a different place on the other end of that Great Circle route. And avgas became unavailable in Fairbanks, and all of that traffic shifted from Fairbanks to Anchorage, which you can imagine had a pretty significant economic impact on Fairbanks at the time, and also played into the eventual demise of fuel refinery in Alaska. So it still has an effect on all of us, because we don't do much of that anymore, if any. I don't think there are any operating commercial refineries that sell to the general market anymore. So all of this information has traditionally been about representing this on paper, and our most familiar format of representing things on paper is a Cartesian coordinate system. So things that are represented in a two-dimensional system, we typically denote with X and Y. You'll also see things marked with E and N for east and north. I don't know why everything isn't easting when sometimes you're moving west, but there you go. These systems originate from the lower left corner and are marked out in the north and east directions. So when you try to apply these over a large area, obviously you're going to have significantly more distortion. So most of these systems are specifically selected for localized regional systems, or they're done in an interesting way so that that distortion is limited, right? So here we show the distortion of your map in going from the sphere to a plane is going to be different over the surface of that map is also going to be different based on how you draw that projection, which I don't know if I included. I don't think I talked about the projection light source, but for this example, you're looking at projecting from the center of the Earth, but there are also models that look at, say, light that comes in perpendicular to that entire surface, and so projects a little bit differently than this projection model. So there are dozens of different types of projections and hundreds of different projections available that each represent your data differently and can serve different purposes. So these are the three main types of projection systems. Mercator being the common example of the cylindrical source model. The conic projections are frequently used, both conic and planar projections are frequently used towards the poles, but also used in other parts of the world. But you can see, for obvious reasons, they help represent, especially the conic helps represent things around that longitudinal center a little bit better. So each of those types of projections has a trade-off. So you can't have any one perfect system other than making 3D globes for everything. So you're going to have trade-offs in your decision making. So the Mercator system is a conformal system. So that is going to try to optimize continuous angles and shapes. And I think that's one reason that it's persisted for so long, is it's become a really familiar way to visualize our world map. But when you actually start to apply that system and use it in any kind of functional process where you're, say, trying to measure distances or calculate areas of countries or other spaces, you begin to see that that map system severely distorts the pieces of key information. Equal area is another really common type of projection that's used because it's less distortive of some of the key aspects of what we try to visualize when we look at a map, right? Usually, if you're just looking at a map on a wall, you're not necessarily going to sit there trying to measure distances off of that map, because typically scale doesn't allow that, especially when you're talking about world maps. But our eyes are actually really good at picking up on distinctions in area. So equal area projections try to optimize that aspect of modeling the Earth. And then there are directional optimizations, and then there are some that are just really interesting or bizarre, specialized. So when you start to put this in to GIS, and I actually lied in that, well, that first sentence is not necessarily true, depending on how you have ArcGIS set up. Well, ArcGIS is always going to open a new map with a projection system. You can define that before you start to put data in it, or you can let your data define that, and we'll get into that more when we start playing with the lab. But just know that going in, it's better for you to control the projection system of the projection displayed in your GIS system than to allow weird, funky things to happen in the background that you don't have any control over. So for ArcGIS, the first data layer that you add, unless you have otherwise changed this setting, will define the coordinate system and the projection that you see in your map. So in our lab, They don't really go into it in the lab instructions, but in the instructions in our GI or our site, our Google site, I have asked you to look at that before and after. Look at what your default system when you open a new map is, and what your system is after you add your first layer, and understand that relationship and how that could affect, you know, if you're planning to do a map in Alaska Albers, which is the projection system used by most of the state data, but you start out adding data from Google Earth, your map is going to be in WGS84, and all of your data is going to be coming in Alaska Albers, and your GIS system is probably going to fix that for you with what we call on-the-fly projection, but it's going to have consequences when you start to manipulate that data and make measurements and transformations. So it's something that's really critical at the beginning level of using a GIS system to understand what those mean and what they mean for your data processing. So that's about as far as we're going to make it today. We're going to get into specifics of different type of projections next week, and you'll get a kind of a preview taste test of it in your lab. But to wrap up, what's the best map projection? I think I told you what the worst was. The answer is this question is a little bit meaningless. There are best projection systems for different types of applications, different places in the world, different times of day. That's not true, but you can see it really depends on what you're trying to do. So we'll get into some of that selection next week.